This is the design of a systems engineering handbook to integrate science experiments with the ThinSat payload. The reason why experiments need space is that microgravity and vacuum cannot be recreated on Earth. Current ground facilities do not accurately simulate the performance the same way it is observed in the space environment. This can only be accomplished through actual environment testing rather than simulation. The International Space Station performs over 2,000 microgravity experiments. These experiments and research as a result has led to development of vaccines and treatments of dementia, cholesterol, cystic fibrosis, as well as stem cell therapy for use in individuals with heart failure. Additionally, material science experiments through exposure of extreme environments in space have led to the development of technologies with preventative corrosion for oil and gas lines on Earth. A new iteration of satellite technology called small satellites, which are classified as satellites weighing less than 500 kilograms, have shown great interest to commercial sector for satellite launchers. Over the past decade, almost half of the total satellite launches involved small satellites. However, only a small fraction of those satellites were dedicated to scientific research. As the number of small satellite launches continues to increase, this reveals an untapped research market for utilizing small satellites for space-based applications. Taking a look at one small satellite in particular, which is called a ThinSat. This is classified as a pico satellite, which weighs less than 1 kilogram, run by the Virginia Space Flight Authority program, which has secured a payload capacity in the second stage of the Antares rocket. So ThinSats will be launched during the second stage of the Antares rocket, which is around stage 9, where ThinSats are released between 200 and 250 kilometers. ThinSats can be launched individually or grouped in sets of 3 or 6. So following the ThinSat development program, a scientist leveraging these ThinSats will have to design their experiments and develop the payload and integrate that with the model and perform rigorous amounts of testing and meeting several requirements that are constrained by the design of the satellite, since it is constrained by mass, power, and size. Additionally, Virginia Space Program also involves other stakeholders which perform testing and provide additional requirements and facilities that the scientists would have to comply with. The ThinSat development process involves several operations spanning from management, systems engineering, and an extensive knowledge of hardware design and software, as well as integration and testing. This poses challenges for scientists leveraging ThinSats for their scientific missions because they have to optimize that space, the constrained space of mass, power, and volume, with the capabilities to perform the experiments within adverse space environment. So you have sources of payload effects coming from the rocket, such as vibration and sound pressure, and during orbit, such as thermal cycling and decompression. So the problem at hand is that these scientists who are experts in their fields of study are not experts in designing, integrating, and testing science experiments for these small satellites. In this way, there's a knowledge gap and therefore a need for some kind of design methodology to provide those scientists with a framework for being able to integrate their experiments with the ThinSat payload. So the concept of operations for a ThinSat payload mission to be used for science experiments is several processes that are outlined in a systems engineering handbook, spanning from project plan development, running simulations, developing those requirements based on the simulations, designing the experiments, performing trade-offs, conducting safety, hazard analyses, integration, and rigorous testing, as well as technical reviews such as the preliminary design review and critical design review required by Virginia Space, and a series of deliverables and documentation such as detailed design reports. The main requirements for this handbook is that the handbook should provide all of the methodology and processes to generate all of those deliverables mentioned in the previous slide. Also, the handbook shall provide guidelines and methods that comply with managing a ThinSat mission according to the design constraints, such as mass, power, and size. From the requirements, this led to the design of a 3-phase development process. This process follows the Virginia Space program, which is also in 3 phases, where in each phase you have the scientists working with the design engineers as well as integrating their designs and the payload with Virginia Space, Twig Space Lab, and launching at the Mars Spaceport. So this cross-functional process diagram shows the iterative and complex processes in each phase, and there's a lot of handoff with the tasks. Therefore, we've also embedded this model-based system engineering tool to provide lifecycle management for the ThinSat mission. This is the form of a web-based system engineering tool which supports requirements management and traceability between requirements and deliverables through modeling, such as IDEF0 diagrams, action diagrams, as well as project management to develop schedules and show critical path analysis and cost analysis. So this ultimately decreases the time for technical reviews because it provides a means for information exchange that replaces manual documentation. The verification of this process design shown in the matrix, all of the processes and the deliverables mapped to each one. In order to validate this process, this handbook was used to aid in the process of designing, integrating, and testing a custom ThinSat payload to be launched on the Antares rocket. This was a multidisciplinary effort between systems engineers, electrical, computer, and mechanical engineers who followed the methodology in this handbook as well as using the model-based system engineering tool to successfully accomplish designing 3 experiments and integrating it with the payload. So some of the methodology provided by the handbook, such as this hazard analysis, where the hazards for ThinSat in orbit are identified, and then those hazards, the root causes are identified through this failure modes and effects analysis and linked directly to the component, and from that we're able to generate control methods to reduce and mitigate those potential failures. Another key method of this process is conducting a multi-attribute utility model. The experiment design involves complex design decisions to trade off mass, power, and size constraints with the experiment design. So this model was used in the case where the design decision was to choose between different kinds of materials and different kinds of sensors. So using an analytical hierarchy process, the decision was decomposed by different measures, including reducing the mass, increasing accuracy, reducing the thickness, as well as increasing the strength of the material, ultimately to achieve the goal of designing this thermal shield for the ThinSat battery. Using the analytical hierarchy process, the weights were calculated, and with the weights, the utilities of each alternative were calculated and ranked according to each measure criteria of the design, and cost was factored in with the respective utility shown in this cost versus utility diagram. So what the product is a systems engineering handbook, which provides the methodology to produce deliverables such as requirements, documentation, trade-off analysis, risk assessments, safety analysis, and verification validation reports. It comes with system engineering consultants who work to manage the ThinSat database through the model-based system engineering tool, which is Innislate. This would cost a scientist about $20,000. And using projected forecast of small satellite launches over the next 10 years, where 15% are dedicated to scientific research, the target market penetration for this business model is 5% of those launches, which yields a total sale projection of about 400 launches in year 10, generating revenue of $34 million, costing about $7.5 million, where the company would break even somewhere between years 4 and 5. Lastly, I'd like to acknowledge all of the members of the team from the engineering departments, as well as the technical monitors and advisors who aided and assisted in this project.